Welcome to another episode of Environmental Digest. Today, we are going to talk about a groundbreaking new technology that promises to clean our water from some of the most stubborn pollutants out there. But it also reveals a really surprising lesson about what it means for something to be truly green. So, let's start with the problem. You've probably heard of these things called forever chemicals. These are nasty pollutants like PFOA, that's perfluorooctanoic acid, and they're called forever chemicals for a reason. They just don't break down easily, not in the environment and not in our bodies, and they're linked to some serious health risks. Getting them out of our water supply? Yeah, that's a huge challenge. Now, meet the potential hero of our story, the electrified membrane, or EM for short. This is a brand new kind of filter, and it's made from a material called Ti-407. That's Ti-407. The whole idea is that it uses electricity to literally zap and destroy pollutants like PFOA. It was designed to be super energy efficient, which, on paper, makes it seem like the perfect solution. But that brings up a really important question. Just because a new technology is really good at its one main job, does that automatically make it better for the planet overall? Well, to find out, researchers did a full cradle-to-grave analysis, looking at its entire life cycle. They compared this new EM technology to the current standard, which is a two-step process called ultrafiltration nanofiltration, or UFNF. And here is the first kind of stunning result they found. To remove just a single gram of PFOA from the water, this new electrified membrane process generates 19.7 kilograms of CO2 equivalent. And here's the twist that really caught everyone by surprise. That conventional method it was supposed to replace, well, it only produces 8.6 kilograms of CO2 to do the exact same job. We're talking less than half. So what is going on here? Why does this innovative, supposedly more efficient tech have a much, much bigger carbon footprint? Okay, to solve this mystery, the researchers really had to do a deep dive. They broke down every single stage of both processes, from making the parts, to running the system, to getting rid of it at the end, to pinpoint exactly where all those emissions were coming from. So let's take a look at the data. On the left, you've got the impact of the new electrified membrane. And that huge orange bar, yeah, it's pretty much impossible to miss. It shows that the overwhelming majority of its carbon footprint, over 86%, comes from just one stage, operation. Just the simple act of running the filter. Now, what's really fascinating here is we can zoom right in on that operation phase. And when we do that, we find out it's not the energy for pumping water that's the problem. No. Instead, there are two kind of hidden factors that are driving almost all of the environmental cost. So here's the deal. While the EM filter is really good at moving water, the chemical reaction it uses needs a little help. It needs something called a supporting electrolyte, basically a chemical you add to the water to help it conduct electricity. Well, it turns out the production of that chemical alone is responsible for 2/3 of the entire process's carbon footprint. And then the electricity you need to power the actual chemical reaction adds another 21%. But you know what? This discovery isn't actually bad news. In fact, it's the opposite. Because by identifying these specific hotspots, the research gives us a crystal clear roadmap to make this promising technology truly sustainable. Let's see how. And this right here illustrates the first and honestly the most powerful step. The original lab tests used a chemical that worked but had a really high carbon footprint. By simply swapping it for a much more common, cheaper, and greener chemical like sodium sulfate, the total carbon footprint just plummets by over 55%, all the way down from 19.7 to 8.8 kilograms. And the improvement doesn't even stop there. The original lab tests also used a very high concentration of that chemical. What the research showed was that by also cutting the amount of this greener electrolyte by 95%, down to a level that's still effective, the EM process finally becomes the cleaner, more sustainable option we all thought it was. The second key is the electricity source you use for that chemical reaction. If you run the system using power from a typical global grid, which still relies heavily on fossil fuels, you get one result. But if you power it with 100% renewable energy, like from solar or wind, you slash the remaining carbon emissions by another third. This table just puts it all together. It shows the incredible potential when you combine these strategies. Using a greener chemical, optimizing how much you use, and switching to renewable energy doesn't just make it a little better. It can cut the overall environmental impact by up to 99%. Now that's how you deliver on the promise of a truly green technology. So the key takeaway from all of this isn't that this technology is a failure. Far from it. Instead, this is just a powerful lesson in why it's so important to look at the entire picture when we talk about sustainable innovation. As the researchers themselves put it, this kind of deep, cradle-to-grave analysis is absolutely essential. It allows us to find and fix the hidden environmental costs of a new technology before it gets rolled out on a massive scale. It lets us optimize for true sustainability, not just one single performance metric. And that leaves us with a critical question. And it's not just about water filters, but for all innovation, really. It challenges us to look beyond just what a new invention does and to ask, what is the true cost from beginning to end? And how can we design for genuine sustainability right from the very start?